Hello, today we're going to talk about principal open subsets of the spectrum of a ring. So let's take a ring A and let F be an A, and we define D of F. So that's what we're going to talk about for basically the rest of the video. We'll also see a little bit else, but this will be quite important also in the following. So we let this be the spectrum, which I will call X later to not so that I don't have to write that much, and also I won't write the ideal generated by F, but just V of F. So that's how we define it. That's clearly open because it's the complement of a closed set. Now let's see what properties do we have for these sets. So we have complements of closed sets. So we have X minus and then V of F union V of G. So we have this definition, and then we just apply De Morgan's rules, and so we get that. Then we apply properties of the Zariski topology, which gives us V of F times G, so that's D of F times G. Okay, so it's the intersection of two principal open subsets is also a principal open subset. So maybe let me write it. So we call these principal open. Okay, and now what's even more important is that they form a basis for the topology. So let's take an open set U to be the complement of a closed set, and M just some subset. Let me write it for M subset A, and then we get that U is equal to X and then minus, and then we can take just the union of the F in M, and again we apply properties of the Zariski topology, so we get the intersection of F and M and then V of F, and well, then we take apply De Morgan's rules, so we get F in M D of F. So that shows us that any open set U is the union of principal open sets, so they form a basis of the topology. Okay, so that's that. And now let me state one more lemma. We will prove just a part of it, and we'll prove the second part in another video. So actually what interests us is, well, we're interested in both, but what's more interesting for the principal open sets is the second part, but we'll see the first part as a so it's kind of similar, so at least a statement. So we have this map spec pi from spec A modulo the ideal little a, and then to spec A, the spectrum of A. So this is induced by the quotient map pi. pi, and the statement is that this is a homeomorphism onto the image, and the image I claim is V of A. That's the first statement, and now let's see the second statement, which involves principal open subsets. So now we look at the map spec and then of A localized at F inverse, and again in the spectrum of A, and this time we take the map induced by localization. And now the claim is that this is an open embedding. And what's the image? The image I claim is the principal open set D of F. So let me write it again. So that's spectrum of A minus V of F. Okay, so let me put this here. Okay, that's the statement, and now let's prove the first part, and we'll see the proof of the second part in another video. So first note that we have, well, ideals in this ring correspond to ideals in this ring which contain little a, and the same holds for prime ideals. So prime ideals on the left hand side correspond to prime ideals on the right hand side containing a. And well, I already mentioned that the induced map is continuous, so we get a continuous map. So the map is a continuous bijection from prime ideals in A mod A to prime ideals containing A. And prime ideals containing A, that's clearly V of A. So we have a continuous bijection onto the image, but we want a homeomorphism, which means that this map should be closed, or, well, the inverse map from the image should be continuous, which means the map should be closed, as this set is closed. Okay, so we need to show that spec pi is closed. So let's do that. Let's take some closed subset in the spectrum of this A mod A, and let's take, say, B to be this ideal of, so y is equal to V of B, which is the set of, let me write it in a new line. So that's the set of prime ideas in this ring here, such that B is a subset of P. And now this B corresponds to a prime ideal in A, so a prime ideal in capital A containing little a. So that gets mapped to the primes in spec A, such that, let's say, B plus A is a subset of P, where so that's, well, B lives in this here, so that's not exactly what it means, but there's a unique ideal containing A which gets mapped to B, and under this map, so from the spectrum, we get this. So that's exactly so. That's again of the form V of, let's say, B plus A. And of course with B plus A, again, I mean this ideal under the correspondence of ideals in. Let me write it so. Ideals in here correspond to ideals containing A here, and that's what I mean here. Okay, and so that means that this map is closed, and that proves the first part, and so proof of 1 and proof of 2 next time. Okay, that's it for that video. So we'll probably prove a little bit more about principal open subsets, and then probably we'll hear a little bit about sheaves, so that we can use these principal open subsets to define the structure sheaf of the spectrum. So later Spec A won't just denote the topological space, but it will denote the topological space with a sheaf on it, and then we'll introduce the category of locally ringed spaces and stuff like that, but you don't have to understand this at the moment. We'll come to that. Okay, that's it for now. Thanks and have a good time. Bye.